Hi there, my name's Cameron. I'm here to talk about reliable filtered data replication. So this is continuously copying from one place to another. And in particular, this talk is going to be talking about our problem and how we replicated data globally at Shopify, read-only data. But I hope to make it interesting for people who've never built data replication, never planned to. And so there's some broad topics discussed and hard problems around data replication that I find really interesting. I've worked at Shopify for about 6 years now. I work on the database team. There's 40 something of us. And I want to call out that I built and designed this with really smart people. So lots of contributors. And there's some not mentioned here that still contribute. I'm going to talk about the background, Shopify data replication. I'm going to talk about our specific problem. Like I said, this talk is focused around our problem and our solution. And then when we get into the design, I'm actually going to focus on 3 hard problems. They're the ones that we spend the most time on, put the blood, sweat, and tears into. And I find they're kind of can be a little bit ignored when there's discussions about this. And I think they're really, really important. And I also think they're super, super fun and interesting. So I hope you agree. Some background on Shopify. There's lots and lots of databases, primarily MySQL. We have a monolith with this custom sharded MySQL implementation. There's a talk about that. And there's hundreds of shards. It handles 20 million queries per second. These numbers were from last Black Friday, by the way. 200,000 transactions per second. Largest tens of terabytes. So quite large. And this last stat's from my coworker, Alex. I think it just kind of shows scale of computers. Quite impressive. Really fun. My favorite part is that the bad problems, they happen like so fast. So if you deploy it in a safe way, you can learn so much just by being in production. Some background on data replication. Like I said, continuously copying data from one data store to another, usually to make data highly available. So performant, reliable, up all the time. If you want to think of a narrow scope, you can think of a database replica, horizontally scaling reads, allowing you to fail over your writer. If you want to broaden your scope a bit, for the people who have used Apple Notes, you can write into your Notes app, writes in a SQLite, replicates, and then on your computer, same Notes app, same local experience. You can also think about running search. And so you want to replicate data usually from a transactional database into an inverted index. Again, data replication. So lots of different use cases, but at the end of the day, it's so that users can have a great, fast experience. And it's very, very necessary. The best ones are super magic. You don't notice it. And that's always the intent with great infrastructure, right? So, human version of our problem. We are interested in making a really fast read-only database. We also wanted to we wanted to put all the data in various places to make the P90 100 milliseconds of reality in all these different countries. And it would cost too much to put all the data there. So we wanted to somehow filter it and store less data there. And then there was a replication throughput and replication lag. Fast reads and fast writes are competing dimensions in a database in physics. And also in a database, fast writes and replication throughput can be competing. So we optimize for checkouts per second. That means that in some cases we're having replication lag. So if there's a way to filter and replicate, that would save a lot of headaches. So the technical version of this, we won't have time to go in the pros and cons of these different decisions, but we needed filtered partial replication, partial snapshots storing a subset of tables and columns, not just the changes that are happening now, but the historical stuff. We wanted P99 of under 5-second replication lag. We needed transactional consistency. So developers, when they decide whatever they decide to include in a transaction, on the source, we want that to be the same on the target to remove any inconsistencies. We needed to be 100% correct. That's obvious, but we actually wanted to prove that we were correct. And there was some desire to do some stateless transformations. So fast forward a bit, skip the boring design stuff. Don't worry, I'll talk about that. But shops are always replicated everywhere. This is the current state. We have this map shows readers, shows regions that we replicate to. You don't have to configure it or care. If you use Shopify, you get the performant, fast storefronts everywhere in the world. You can have a global, presence. With many writer regions, many more reader regions. This talk, like I said, focused on the reader regions. Response times were cut in half when we deployed the data there. So skipping this network hop to the US, or many network hops to the US, reduced the response times quite a lot. And we also did it with really low replication lag. These flash sale events that were causing lag in the past no longer do. So why not filtered replication? This is kind of the obvious alternate approach, and I don't have time to talk about all of them, but there are many, like always. We use MySQL non-filtered replication all the time, and it's amazing. MySQL filtered replication isn't a complete solution. It doesn't offer us a way to do these partial snapshots, grabbing just like tables and columns we care about. Also, if you think through the process of like having this evolving schema on the edge, for example, you're replicating the products table and the orders table, and you need to add images table now. It's like, okay, we have to like stop the replication, restart with new configuration. There's ways to update it live, but then you have to think about the correctness around grabbing the backfill data and putting it in. And there's different complexities. Basically, you end up with a very complicated system instead of a single process. And if you think about in reverse, which I like to do, is like you have a single process doing this. Would you take out what is the simplest part, which is reading the bin log and writing it? All the problems we're going to discuss today are not reading the log and writing statements. It's all the problems around replication that are the difficult part. And so we decided to not go down this path, but I'm sure with the right infrastructure and you could see a solution working this way too. Excuse me. So our solution, we replicate, so source MySQL in a region. We replicate through backfilter, which is our Go process. We read bin logs and we write into a MySQL. We write statements into a MySQL in that region. So very contained process here. And then we use MySQL replication to distribute that filtered data all over the world. Like I said, we can do these partial incremental snapshots, so grabbing the data from the source. I'm going to talk about that in the next slide. And we use the GTID to persist this progress and for crash recovery, panics, any deployments or updates. So we need a way to grab the historical data, right? So you can't just start processing the changes and ignore that there's many years, in our case, sometimes decades history of data in the database. So you have to have a way to grab all that. Then the naive way would be do a select star. That doesn't work when you have massive tables. The default in Debezium is to open a transaction and then chunk through because you get a consistent state. That doesn't work because if the transaction's killed, you lose your progress. The MySQL history list length grows, tries to keep that constant state in sync, and that causes production problems. And more rows end up blocked, and you can't do schema changes. And so right away, that was off the table. We designed at Shopify this algorithm that's a read-only version of a dblog algorithm where you take the current transaction, you do a chunk, you take the next transaction, and then you see that the changes, the primary keys in that happened in the bin log since that batch was running. So it's like, oh, these ones were in here too. Now we're going to deduplicate them. So it's quite simple conceptually. We contributed this to Debezium. We don't actually use Debezium for this. We use Go MySQL Canal, which is a great bin log parsing library, but we implemented this algorithm. The other thing that is kind of a niche thing is that a lot of these systems, they'll like do these backfills in the same stream as the bin log. That's not possible for us because it causes replication lag. And so we actually do them in parallel, and where we can do many backfills at once. All of that, by the way, have evolved to be the case, right? It's not like you go out and design like the complicated system from the start. These were all evaluated based on the impact and the SLO breaking and replication lag. We want it to be better. Now I'm going to talk about these 3 hard problems. So my favorite, correctness, right? You're never going to be 100% correct. Unfortunately, when you're dealing with replication, that means data corruption. So we made a condition that for a write to be completed, it had to be checksummed, it had to be verified to be correct. And this became the most essential part of the system. It built so much trust within our team, but externally as well. And it allowed us to develop way faster. I'll talk about that a little bit more later. There's 2 general approaches, full table verification and incremental. We start with incremental, which is basically like you write the data in, you send reads to both the databases, and you make sure the checksums are the same. This, when well designed, doesn't interfere with your replication because you can do it asynchronously, and reads are faster than writes. Sometimes things change so fast, you have to keep trying and you have to back off. It can get quite complex. And we ran with that for a while, and we actually just recently also implemented full table verification. These have different trade-offs, right? Incremental, you get more efficient, you're wasting less work, faster feedback, but full table verification can detect problems that actually exist external to your system, which can be a really important thing we've discovered. So, consider which one you want to do. At Shopify, we've also implemented like some request level verification systems, but overall, these verification systems are amazing, and where you decide to implement them and how can be very important, and it takes a lot of time, but I think it's super, super worth it. So hard problem number 2, schema changes. Shopify does 10 schema changes per day. We couldn't ignore it. Schema changes are features, right? So developer velocity is around shipping changes, shipping features, shipping schema changes. We need them to be fast. At Shopify, we use an online schema change based strategy. We want to talk about our schema changes more in general, but essentially, we're making the changes to an empty table, copying the data in, and then doing an atomic rename. This is how we do them with no downtime. Very difficult problem. This is talking about how we integrate the online schema change to the database itself with this replication system. And so instead of the app actually making the changes directly to the database, they send that to the manager, what we call manager, which manages all the deployments of these backfilter processes across all of our shards. And it can trigger an actual schema change to happen. So let's say we add the products table. It will create table statement. And then backfilter, manager will update in the config and say, now you want to copy this table. And so add it to set. And then backfilter will go and grab all the historical data and then add it to its bin log stream. So backfilter is really dumb. It just knows I have to copy these tables and columns, and it does it. And manager is like a state machine that orchestrates it. And this pattern worked really, really well for us. Oh yeah, the other thing I'll say about schema changes is that I gave a simple example. All the various schema changes are slightly different, but you can imagine a similar process where there's 2 things: changing the database or filling up with data. Sometimes you don't need to fill with data like a drop, but yeah, they all work with a similar pattern. So write performance, the last problem I'll talk about here. Basically, we broke our SLO on some databases due to write performance. Like I said before, we started with reading the bin log and writing statements sequentially. That means super simple, super hard to get wrong. I very much recommend starting that way. But you're limited by Little's law, right? So you can probably easily calculate how many transactions you can write per second if you're writing sequentially. And we reached that limit, but after some little bit of time in production. And so you can't just do parallel writes naively. You have to think about how these different events correlate to each other. And so we tried to implement parallel replication properly in Go with statements. So MySQL already has parallel replication. The default algorithm in MySQL is called write set. There's a few algorithms. Write set's basically like if the first transaction has these sets of unique keys, including the primary key, the second transaction also has some of those or one of them, then these transactions are dependent on each other. If they're touching completely different keys, then they're independent. And if they're independent, that means we can apply them in parallel. And so what I really like about this algorithm is it kind of inherits some of the decisions in the original client, where it's like, okay, these different clients or these different sessions are writing to MySQL, they're touching different keys, they're doing it in parallel. Well, the replica can do that too. And so as a developer, if you want to keep that consistency, you include it in a transaction or tie the transactions together in some way. And so you have the flexibility and you have the performance there. And we wanted to learn from this. And so we tried a couple things, eventually implemented this parallel replication write set algorithm in Go, still writing statements, but using this for dependency tracking using this algorithm. And it brought our replication lag from P99 of 5 seconds and breaking this to the P99.9 of under 1 second. And so if you think about it, like you get this large chunk, big transaction, it's doing a lot of things. It might take a couple seconds to write in some cases. Well, it doesn't block, other critical things going through. And we find that apps behave very similar like this, where you'll have, these background jobs, these processes that need to run, these bulk actions. But the true interactiveness needs to be really fast. It can always be unblocked and write. And the verification, we leaned on this heavily to ship this. Without verification, we couldn't have shipped this and numerous other refactors and changes, because we knew right away when we had a bug. We had like 4 or 5 interesting bugs with parallel replication. And we could lean on the verifier to know when we had completed it and were able to ship to production. So speaking about the solution here again, and summarizing, we built a system since our first ship to production. It's been about 2 years. We're completely deployed now. Almost every shop is using this, and it's the default way that we replicate data at Shopify globally. We have, this reduction in response time for buyers. Our queries are very fast in these databases, P50 of 300 microseconds. That's just InnoDB being InnoDB. We don't have these blockers about replication lag and costs anymore, hence why we've deployed to these different regions. We have some flexibility in the future, so we need to continuously replicate some subset of data for whatever purpose. We can use this. But there's some downsides, right? So, one schema is simpler to reason about than 2 schemas for developers, and it adds more toil. So you always have to think about that if you're splitting up a monolith. The operational complexity is higher, right? So there's people working on this. When you're using a database replication, you're inheriting years or decades of blood, sweat, and tears from very smart people focused on this topic. And so you're going to have to sweat. You're going to have to bleed a little bit if you want to implement it yourself. And just last week, we had a backfill issue, for example, that caused some lag in particular situations. And this is something you're working on, right? Constantly. So that's something you have to think about. And it's, for us, it was a very critical and important thing to do. So it was worth it, but sometimes it might not be. Here's some bonus personal learnings. Data verification improves trust and development speed. massively increase our development speed. We could ship so many things we'd be too nervous to ship because of verification. It's amazing. However you want to implement it, if you can do it, I highly recommend it for lots of different systems, but especially replication. And the trust internally and externally just grew so much because of this. There was like a well-designed replication system, it should be bottlenecked on write performance. And so, using a faster language or something like that, optimizing Go in some extreme ways probably won't work. You can't make stupid decisions, but at the same time, like you're not gonna get a lot of wins there. Just monitoring the write ahead log itself, or the bin log in our case, is so useful for monitoring the database. You can see details about transactions, what's happening, who inserts, who's doing things, etc. It's so useful to just know the truth about what's happening to your database on the right side. Obviously, there's lots of read side things you need to monitor too, but I really want to improve our monitoring of the bin log. Well, thank you for listening to all of this. I'm sure I'm going to be live in the chat answering any questions, so hit me. And also feel free to reach out on these channels and come work for us at Shopify. It's an awesome place to work. You get to deal with really fun problems and awesome people. Thank you very much, everybody.